Hey everyone, so today we're going to be learning about the product rule. So to start out today's lesson, let's look at an example instead of getting into it right away. So let's say we have the function f at x equals x plus 5 times x minus 2. So using our prior knowledge, the first thing that pops into mind after, oh no, is to expand it and then find the derivative using the laws we learned in the last lesson. So let's try it. Let's expand it. Minus 5 times 2 is 10, minus 2x, and that equals to x squared plus 3x minus 10. And that's what we get if we expand. So using the laws of derivatives that we learned, the derivative of this would be 2x plus 3. That's what we get. So the answer we end up with is 2x plus 3. Personally, expanding polynomials was the most annoying thing for me in grade 11, and that's exactly what today's lesson is about avoiding. We're going to use something called the product rule to save our time. Simply put, the product rule goes like this. If you have two functions that are being multiplied to one another, as in the example that we just saw, then to arrive at the derivative, you need to multiply the derivative of the first function with the second function and add that to the derivative of the second function times the first function. It's a mouthful, but this is what it looks like. H at x equals f at x times g at x, so h prime x would equal to f prime x times gx plus g prime x times f at x. So let's put the product rule to use in finding out the derivative of f at x equals x to the power 3 minus 2 times x plus 5. As you can see here, two functions are being multiplied to each other. So what we're going to do is find the derivative of this, multiply it by this, and then add that to the derivative of this multiplied by this. So let's do it. So f prime x would equal to 3x squared, and this doesn't have a derivative, so we're just going to multiply this by x plus 5, plus the derivative of this is just 1. So we're going to... Alright, so now we have to multiply this. And 1 times this doesn't really change anything. So collecting like terms, we get and that is the derivative. You may ask, if the rule with adding and subtracting functions is just adding and subtracting their derivatives, then shouldn't the product rule be the same? No, it's not, because clearly if we did this, we would arrive at a completely different answer. Okay, so let's say that we have the function f at x equals x plus 1 times x plus 3. Okay, so we know that if we were to expand this, we would get, a function that is, something to the power of 2. So it's a degree of 2, which makes it a parabola. So we know that, if we were to multiply the derivative of this but times the derivative of this, it would just be 1. Like we would get 1, which is a horizontal line. But if it's a function with a degree of 2, then from the rules that we know before, it's impossible that its derivative would have a degree of 0, as in be a horizontal line. No, it would have a degree of 1, because, the derivative is always 1 degree lower than the original function. So now we need to prove the product rule to see where it came from and to make sure that it's actually legit. So we know that by definition, the derivative of f at x equals to the limit as h approaches 0 of f at x plus h minus f at x all over h. So if h at x equals f at x times g at x, how do we use limits to, find the derivative? So it's going to look something like this. The limit of, as h approaches 0, of f(x plus h) times g(x plus h) minus f at x times g at x. So here, the only thing that was different was that I multiplied f at x by g at x over here, so it's a bit longer. Okay, so now what, I'm going to do is add something in the middle. It's not going to change anything because I'm just adding and subtracting it, but it's just going to help us arrive at the proof. So I'm going to be adding minus f(x plus h) times g at x plus f(x plus h) times g at x. Oh. And then the rest of the function, which is minus f at x times g at x, and all of this over h. Okay, so the next step is to factor these separate parts. So from here to here, we're going to factor out f(x plus h), and from here to here, we're going to factor out g at x. So now it would look something like this. F at x plus h times g at x plus h minus g at x all over h, and then plus g at x times f at x plus h minus f at x all over h. Okay, so now we're just gonna rewrite this as separate limits. So we're gonna write the limit of this times the limit of g at x plus h minus g at x all over h plus the limit as h approaches 0 of g at x times the limit as h approaches 0 of f at x plus h minus f at x all over h. So as h approaches 0, in this case, it's just going to leave us with f at x. And as you'll notice that this part, by definition, is the derivative of g at x. And this part over here, by definition, is the derivative of f at x. In the end, what we end up with is f at x times the derivative of g at x plus, because there's a plus sign there, g at x times the derivative of f at x, which is the product rule. So here we have the product rule. Okay, so now that we know where it comes from, let's try a slightly harder example. So if we have f at x equals 3x to the power 5 plus 10 times 4x to the power 6 minus 20, how would we find its derivative? So we know that we need to find the derivative of this first, just to start off. So this would become 15x to the power of 4 times 4x to the power of 6 minus 20, plus the derivative of this, which is 24x to the power of 5 times, 3x to the power of 5 plus 10. So that's the derivative that, not simplified. So to simplify it, we will have to expand it, but it shouldn't be too hard. So let's do it. It's not really a hard example in my opinion. The only thing here is that it uses slightly bigger numbers, but that shouldn't really scare you because in the end it's still the same concept. I mean, if you need a calculator for this, go ahead and use it. So to expand this, we're going to have to do 15 times 4, so 60, and then add these together, minus 15 times 20, which is 300, x to the power of 4, plus, now we gotta expand this, 24 times 3, 72, x to the power of 10, plus 240, x to the power of 5. So, now we gotta collect like terms, so 60 plus 72, that would be 132, I think. Wait, let me double check that. Pause it. So yeah, I was right. It's 132 x to the power of 10 plus 240 x to the power of 5 minus 300 x to the power of 4. See, this is the derivative. It's, seemingly long, but, it uses bigger numbers, but we arrived at using the product rule, which, is the same in every situation. Okay, so what if we have a function that looks like this, where, the two functions have a power, in this case the power of 2. Are we going to have to expand this? Well, that would take an extremely long time. So no, we're not going to do that. We're going to use something called the power of a function rule. We are going to use the product rule, but to use the product rule, we need to know what, how to find the derivative of each part. And if we have a part that, has an exponent, we're going to have to use the power of a function rule, which basically goes like this. If you have f of x to the power of n, the derivative of this expression is going to be the derivative of this part times the derivative of the inside part. So, using the rules that we already know about exponents, if we have f of x to the power of n, then the derivative would be n times f of x to the power of n minus 1 times whatever the derivative of f of x is on the inside. So basically what you're doing is you're multiplying the derivative of the whole thing times the derivative of the thing inside the brackets. It's confusing, but we'll use it and then that should clarify it up a little bit. So let's do this. If f of x equals x plus 4 to the power of 2 times x plus 3 to the power of 2, f prime at x is going to be the derivative of this, and we're going to take the 2 outside, and the inside is going to stay the same for now, and then 2 minus 1 is equal to 1. And then we're going to multiply this by the derivative inside, which is just 1 in this case, and multiply this by x plus 3 to the power of 2, as in the product rule tells us to, and then we're going to find the derivative of this. So again, we're going to take the 2 outside, keep the inside the same, and minus 1 equals 1 in this case, and then the derivative of the inside in this case is 1. Multiply this by the original first part, and this is what we get. This is the derivative of this. So to simplify it, we're just gonna erase some parts, so the 1 is not really necessary. So now that we know both the power rule and the product rule, let's try some harder examples. So this example isn't exactly hard, it just looks challenging at first. The trick is to rewrite it. So instead of f at x equals x minus 7 over x plus 7, we're going to rewrite this in a way that helps us use the product rule. So we know that the denominator has a power of -1. So to say this is also to say this, like they're synonymous. So now we know that there's two functions that are being multiplied to each other, and we can use the product rule and the power of a function rule. Okay, so let's do it. The derivative of this is just 1 plus the derivative of this would be -1 x plus 7 to the power of -2 times 1. And then we would just again, you can simplify this by, finding a common denominator, in this case, x plus 7. But all in all, this is the unsimplified answer of this question. Okay, so this example is kind of like the example that we did a while ago, where it was just a bunch of big numbers, but in the end, it was like pretty straightforward. All we had to do was use the product rule, and there weren't any like tricks or anything. So f prime x would be the derivative of this part. Using the rules that we already know about derivatives, it shouldn't be too hard. Power 4 plus 15 times 3, so that's 45 to the power 2 minus 20x times plus the derivative of this, which would be 36x to the power of 5 minus 14 times 4, which would be 56 x to the power of 3, and that would really times the first function. And again, you can simplify this. You're going to have to multiply these two and these two, and it's going to be super, super long, but the answer that you end up with is going to be the derivative of this long thing. So here, the only challenging part would be, I would say, just expanding it and simplifying it, really. So now that we're almost done, here's just a little quiz to end up things and check your learning. So what is the derivative of 4x plus 6 times 6x minus 1 to the power of 2? So here you have to use both the product rule and the power of a function rule. So the answer you should have gotten is 432x squared plus 336x minus 68.